Hi, hi everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of ECE at IARE, Hyderabad. Yeah, today we are discussing about LTI systems, linear time invariant system. Here in this case, where LTI system are a class of systems used in signals and systems that are both linear and time invariant way. So linear systems are systems whose output for a linear combination of inputs are the same as the linear combination of individual response to those inputs. Due to this, time invariant systems are systems where the output does not depends on when an input was applied. With this, so these properties make linear time invariant systems easy to represent and understand graphically with reference to mathematical expressions. This is the main what you call significance related to linear time invariant system. The linear systems are systems whose output for a linear combination of inputs are the same as linear combination of individual responses to those inputs. So these are LTI are a class of system used in signals as well as systems. Signals and systems that are both linear and time invariant purpose. They are using the LTI systems. Here the time invariant systems are systems where the output does not depends on when an input was applied. Yeah, the LTI linear time invariant systems are superior to simple state machines for representation because they have more memory. So of course, we know that our number of systems, some are what you call memory or memoryless, but especially these LTI linear time invariant systems are superior to simple state machines for representation because they have more memory when compared to other systems. Yeah, LTI systems, unlike state machines, have a memory of past states and have the ability to predict the features. This is the major feature of this or significance related linear time invariant system. Have a memory of past states and have the ability to predict the features. Okay, so LTI linear time invariant systems are used to predict long-term behavior in a system. So they are often used to model systems like power plants. So somewhat a real-time purpose. We will use that LTI systems are used to predict long-term behavior in a particular system. Yeah, another important applications of linear time invariant system is electrical circuits. Okay, so in electrical circuits, these circuits made up of, we know that all major components are inductors like capacitor and electronics components like active components like what do you call transistors are the basic upon which modern technology is built. That's why always they are using this LTI system is electrical circuits because of they are expecting real-time solution and some problems will be solved by using real-time system. Yeah, now coming to these properties of the linear time invariant system. Yeah, properties of linear time invariant systems. LTI systems are those that are both linear and time invariant. Linear systems have the property that the output is linearly related to the input. Okay, changing the input in a linear way will change the output in the same linear way. Okay, due to this, properties of the linear system will analyze. Okay, so major properties of the linear time invariant system, like what do you call linear time invariant systems. So here are some properties of linear time invariant systems. Convolution. This is the popular property for other purposes like overlap add, overlap save, and some other concepts. We require this particular property. Okay, communicative property. Yeah, here for the input functions and LTI systems, responses and the following the expressions are valid. Okay, and distributive property. After that, associative property. So each and every property, they have their own features and merits and demerits. Some applications, some solutions purpose. We require some problem defined, problem solving purpose. We require this type of properties. And other one is inversion property. After that, stability property. Using the inversion of stability, the system is stable or unstable. We will decide the factors using the major definition as well as with help of we applying the different properties like inversion, associative, and stability property. We can decide the factor. Okay, now properties of the linear time invariant system. So we can consider somewhat we have to represent that system. The system is discrete time system. Discrete time system. The DTS, discrete time system. Previously we learned that a DTS, where DTS is discrete time signal. The signal input section, here we are having that a system is like this. This is the system. You have to consider the system may be a LTS system, linear time invariant system. That input either CTS or DTS, but here input is here is DTS, discrete time signal. The system is linear time invariant system. We will expect that all output response. Here we have to consider that the system is discrete time systems. Okay, discrete time systems. Discrete time systems is a mathematical operation that maps a given input sequence. Like here we know that where DTS is followed by that x of n. If you are writing that where x of n here, this is where CTS, continuous time signal. But here we are using this parenthesis. This is a discrete time signal. Okay, so here a discrete time system is a mathematical operation that maps a given input sequence. The sequence is x of n, where x of n is discrete time signal into an output sequence y of n. Okay, like using this all example, y of n is equal to here. The system is available, input is x of n. Using this system, we will expect that y of n. So that where y of n is equal to the operator t of x of n. Okay, so moving, or we can consider that all running. We have to calculate that running average, where that may be either maximum value or minimum value or average value or whatever it is. The maximum is y of n is equal to x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3 plus x of n minus 4 and so on. So ideal delay system, that ideal delay system is assigned that where we try to calculate that y of n is equal to maximum of x of n minus 1, x of n minus 2, x of n minus 3, x of n minus 4 and so on. Here y of n is equal to x of n minus n naught. Says what you call in terms of ideal delay system. So with reference to this all discrete time system, we should realize that where a discrete time system is a mathematical operation that maps a given input sequence x of n into an output sequence y of n. Okay. Yeah. Here the memoryless system. A system is memoryless if the output y of n at every value of n depends only on the input x of n. At the same value of n, the time is, we can consider this either maybe a square or sine, or maybe what you call other ideal cases, a digital system or maybe delay system. Like this, we should consider that all memoryless systems. Say for example, the square, where using this system, if it is a memoryless system, input is what you call, that input is x of n. Okay, that output response is what you call y of n. Okay, in terms of the square, where y of n is equal to, here the output response of y of n, where y of n is equal to what you call input is x of n, where x of n what you call square. You can consider this as square. Okay, like this sine. So in terms of the sine, so if you want to calculate that output response with based on the sine, where y of n is equal to sine into x of n. Okay, like this, the memoryless system will observe this system is a memoryless. The output y of n at every value of n depends only on the input x of n at the same value of n. So we will observe that either square or sine, or sometimes what you call counter example. If it is ideal delay system, here where delay system already we have seen that with reference to that, where y of n is equal to x of n minus n naught. This is related to what you call memoryless system. Next, coming to this linear system. A linear system, the system is a linear if and only if that operator t, x1 of n plus x2 of n is equal to t of x1 of n plus t of x2 of n. Okay, additive of that y, and t, that operator t ax of n is equal to a into tx of n, which is the scaling. Okay, so you can consider the simple example where the system, we have to consider that system is ideal delay system. So ideal system, we know that one where y of n, the system is here, that the system is available, where input is x of n. This is a discrete time signal. So the system, based on the system, we will expect that output response. So y of n, where y of n is equal to, so if we are considering that ideal delay system, where here y of n is equal to x of n minus y of n is equal to x of n minus n naught. Like this, if it is signals, input signals are increasing, we can vary that all input signal, we can analyze in mathematically. Okay, like try to calculate if number of delays, first delay, second delay, through based on delays are increasing or decreasing, we can analyze in mathematical notation or mathematical expression. So where t of x1 of n plus x2 of n is equal to x1 of first delay, x of x minus x naught plus x2 of n minus what do you call, okay, n minus n2 and so on. So like this, the operator t of x of n, t of x1 plus n is equal to x1 of n minus 1 plus x2 of n minus 2 and x2 of n minus n naught, where the operator t ax of n is equal to what you call that ax1 of n minus n naught. Yeah, a into t x of n is equal to ax1 of x1 of n minus n naught. Like this, the linear system is linear if and only if the base of the additive y and what you call scaling of that ideal delay system will be observed in mathematically. Here, coming to the next property, time invariant system. Time invariant, you can consider shift variant systems. So it is followed by that output response is verified, y of n is equal to t of x of n, y of n y of n minus n naught is equal to t of x of n minus n naught. The time shift at the input causes corresponding time shift at the output. So like this time invariant shift invariant system will be analyzed in the mathematical notation. Example, here we know the L squared, where y of n is equal to x of n all square. In this case, delay in the input, the output is y1 of n is equal to x of n minus n all square. If it is delayed, okay. Next, delay the output gives y of n minus n naught is equal to x of n minus n naught all square. This is related to the square with the delay the input and the output is verified. Delay in the output gives where y of n minus n naught is equal to x of n minus n naught square. Coming to this counter, like example in terms of the compressor system, where y of n is equal to x of mn. Delay in the delay in the input of output is y1 of n is equal to x of mn minus n naught. Similarly, this delay in the output gives y of n minus n naught is equal to x of m of n minus n naught. Like this, the time invariant system, or we can consider shift invariant system. So you can analyze that y of n output response of the given system is y of n is equal to the operator t of x of n. Okay, a time shift at the input causes corresponding time shift at the output. So using these two examples, like consider the square as well as compressor system. Okay. So if you are using the compressor system, you can decide that all memory less or memory easily can identify using the mathematical expressions. Next, causal system, causal or causal system. Yeah. Next, this is the important property where causal system is causal or causal if its output is a function of only the current and previous samples. Yeah, there is a backward difference where y of n is equal to x of n minus x of n minus 1. We are using this all background. If we are using the y of n is equal to x of n minus x of n minus 1, what happens? It is related to what you call CTS, continuous time signal purpose. But here we are using discrete time signal, discrete time system, discrete time signals, like here y of n, where y of n is equal to x of n plus 1, okay, plus x of n. Like this, we can represent that background difference, or you can say the counter example like forward difference, where y of n is equal to x of n plus 1 plus x of n. Okay. So next, come to the next system or related to the property, a stable system. Stability, we know that all stability, now here our system is stable or unstable, like we can decide. Here in stability, in the sense of the bounded input, bounded output, above, the system is stable if every bounded input produces the bounded output. Because already we learned that with reference to above, bounded input and bounded output, the system is stable if every bounded input produces a bounded output. Here it is followed by in mathematical where x of n, where in terms of this, where x of n or maybe what you call less than or equal to bx less than or equal to infinity. So here it is what you call mod y of n, where y of n, okay, y of n less than or equal to what you call by less than infinity. But here in this case, but in the where stability, in the sense of the bounded input, bounded output, we go, a system is stable if every bounded input produces the bounded output. So that's why we can consider that where this in terms of discrete time system should be a stable system where x of n, okay, mod x of n, okay, less than bx, okay, less than infinity, okay, like this. What do you call mod with reference to output section y of n mod, okay, less than or equal to, where input section bx, the output section is by less than infinity, like this. We can analyze this stability in the sense of the bounded input, bounded output. We go, the system is stable if every bounded input produces the bounded output. Yeah, best example is square. Always we are in the square. We know that y of n is equal to x of n square. If it is log, yeah, if input is bounded by x of n less than bx less than infinity, yeah, if the output is bounded by y of n less than bx square less than infinity, okay, so the time directly we are ready to analyze that output response y of n is equal to log base 10. Log y of n is equal to log base 10 x of n mod x of n. So even if input is bounded by x of n less than bx less than infinity, even if input is bounded. Coming to the output not bounded for x of n is equal to 0, the time where y of n is equal to log base 10 x of n is equal to minus infinity. Like this, using this all simple property, stable system will be appeared. You can consider the square or maybe log, or what do you call, if log is inputting, if input is bounded or output is bounded, yeah, if input is bounded, even by what do you call, output not bounded for what do you call, where x of n or y of n, where x of n is equal to 0, the time output that y of x of n equal to 0, where y of 0 equal to log base 10 x mod x of n is equal to minus infinity, not plus infinity, minus infinity. Like this stable system, we'll evaluate this by using this simple mathematical expressions. So linear system example, here it is using the linear time system, okay, that input of the linear time system, here it is 0, 5 and 0, minus 5, what do you call, 0.5 and what do you call, 1. So here it is, here 0, 1, 2, 3, 4, 5. So here 1, minus 1, minus 2, minus 1. Here it is minus 1, minus 2, minus 3, minus 4, minus 1. So here it's plus 1, 2, 3, 4 and 5. So given to that LTI system, that output response is, okay, we are applying these all properties, we'll explore output responses like this. Next, coming to the next where LTI system, where what do you call that, here it is origin 0, 1, 2, 3, 4, here minus 1, minus 2, minus 3, minus 4, minus 5, given to that the same. So the output response is same or different, we'll try to verify, so and so on. Okay, here now to change this, okay, the output response is like this, okay, where here it is 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4. It is given to here, LTI system response is like this. Okay, so for verifying this type of what do you call output response is, we require that properties. How we are verifying this? This is a manual operation. While practical operation, by using the MATLAB built-in function MATLAB MathWorks, so easy can verify that same LTI system responses with the help of simple properties. Yeah, next coming to the linear time invariant systems, special importance for their mathematical what you call tractability. Most signal processing applications involves linear time invariant system. LTI system can be completely characterized by their impulse response. Okay, that impulse response here maybe in terms of the output response, it will vary where y of n is equal to the t x of n is equal to what you call the summation. Here the summation what you call that k equal to minus infinity to plus infinity, that x of k delta of n minus k. We can consider this as the linear. Okay, so linear time invariant, where the summation k equal to 0 to minus infinity plus infinity x of k into t of delta of n minus k, the summation k equal to minus infinity plus infinity x of k hk of n, this is time inverse, time invariant. Okay, linear time invariant. So finally that summation where that what do you call that summation where k equal to minus infinity to less infinity, where x of k into h of n minus k is equal to what you call x of k, so convolve with what you call h of k. Okay, like that we will try to analyze that mathematical notation for this, especially the linear time invariant system based on the LTI system properties. We'll try to verify here. Yeah, this is the example. If it is x of n is equal to a power e of n, okay, for using this x of n, consider this where x of n here in discrete time system is also equal to a power n u of n for using this all condition for n less than 0. What happens if it is the time or the response of this y of n? So we have to verify using this all graphically. That means where n is equal to what do you call n is substituted 0, 1, 2, 3 and so on up to k. Okay, so like this, if we are using this all for n equal to n less than 0, try to verify here. Yeah, in the second case for 0 less than or equal to n less than n minus 1, the time here the k versus here, it is ready to observe this all and so on. Where y of the time that output response y of n is equal to summation k equal to 0 to n a power k is equal to 1 minus a power n plus 1 by 1 minus a. Okay, like this, that impulse response. That impulse response h of n is equal to u of n minus u of n minus capital N. But here, this case, to substitute this value, where what do you call that impulse response h of n, so is equal to, if it is 1, we have to use that all condition 0 less than or equal to n less than or equal to n minus 1, 0 otherwise. Like this, for if next case for n greater than or equal to n capital N minus 1, so n like this, and finally that output response y of n, where y of n is equal to what you call the summation k equal to n minus small n minus capital N minus 1. Okay, here a power k is equal to a power n minus capital N plus 1. So minus a power n plus 1 by 1 minus a. Finally, that outcome where y of n is equal to, so find like this, where y of n is equal to, okay, so a power n minus capital N plus 1 into 1 minus a power n by 1 minus a. Like this, you can decide that our output response in given input. Okay, like this graphically, we have to like this one. Next, involve these properties of LTI system. Convolution is the commutative. So here, in this case, x of k convolved with h of k is equal to the summation k equal to minus infinity to plus infinity x of k into h of n. Here, x of k into h of n, h of n minus k. It is also equal to the summation k equal to minus infinity plus infinity h of k into x of n minus k is equal to h of k convolved with the x of k. This is the convolution is commutative. So using this solver where input is, you consider this impulse response. System is input impulse response. Input is x of n. It is given to that system. Will expect that output is y of n. Yet sometimes the convolution is distributive. So how it is distributive? Because of, so here where x of k is convolved with h1 of k plus h2 of k is equal to x of k convolved h1 of k plus x of k convolved with the h2 of k. Okay, like this. So that convolution is distributive. h1 of k plus x of k convolved with h2 of k. Okay, so like this, so it is convolved here where x of n, h1 of n and h2 of n, it is added this, we will expect that all like this. Okay, y of n. Due to this mathematical expression, due to this particular property, convolution is distributive. So when we are solving this all problems or problem identification or problem solving, we require this type of what you call properties. Okay, so we will expect this where x of n is given to h1 of n plus h2 of n. We will expect that y of n with the convolution is distributed. Next, cascade connection of LTI system. Cascade connections of LTI systems. So here input is x of n. It is given to that what you call convolutions. What you call the impulse response h of n. The output is will expect and it is given to the h2 of n. We have to verify that y of n. This is all our cascade h1 of n and h2 of n. So cascade connection of the LTI system should follow this all. Okay. Now if it is number of here we can consider that where x of n, h2 of n, h2 of n and h1 of n. We'll expect the y of n. Or we can consider the input is x of n. So how it is cascade? So where h1 of n, what you call convolved with this is 2 of n. We'll expect the y of n. This is the cascade connection of linear time invariant system. This is the major, one more major property. Using this type of property, we can solve a lot of mathematical notation. We can simplify this if it is long analysis of mathematical expression. It is all depending upon system. The time we will minimize. We can represent in terms of this form, like cascade connection of linear time invariant systems. Yeah, next come to the stable and causal LTI systems. Here an LTI system is, you know that one, that is BIVO, binary input, binary output. Stable if impulse response is absolutely summable. Let's write the output of the system as how it is appear, how it is the response of the given system. Then the output is bounded by, how it is bounded with bounded input or bounded output. The output is bounded if the absolute sum is finite, the time how it is affected with this LTI. Then LTI system is either causal or non-causal. If it is causal, if f is how it is varies. So easily can analyze that stable and causal LTI system by with reference to that LTI system is BIVO. Okay, how it is varies. Let's write that the output of the system as, you know that, summation k equal to minus infinity plus infinity x of k less than infinity. This is output of the system as the summation k equal to minus infinity plus infinity h of k less than infinity. Then the output is bounded by what we call like this, where y of n. It is bounded by where normally we are using the y of n, but it is not our case. Here normally they are using the mod, the summation, what you call k is equal to minus infinity to plus infinity h of k into x of n minus k, okay, with mod of this, okay, less than or equal to k value. But this case supposed to you have to use that y of n, okay, in terms of discrete time signal, mod of this. So mod of that here, the summation k equal to minus infinity to plus infinity h of k into x of n minus k, so mod what you call less than, okay, less than or equal to the summation, less than or equal to the summation where k equal to minus infinity to plus infinity, okay, h of k, okay, mod h of k x of mod x of n minus k, okay. So here it is, if the condition is right to apply, if what do you call that what do you call continuous time signal x of n, okay, x of n. So what do you call should be mod of this x of n, discrete time signal. So discrete time signal less than or equal to what do you call bx. After this, the output is bounded if the absolute sum is finite and linear time invariant system is causal. If f, so here where y of n is equal to, where y of n, this y of n, what happens that y of n is equal to y of n less than or equal to bx into the summation k equal to minus infinity plus infinity h of k, okay. Like this an LTI system is causal if f where summation k equal to, so here the k equal to minus infinity plus infinity h of k less than infinity, okay. So finally that h of k is equal to 0 for k less than 0. So based on this you can decide the thing, an LTI system is causal if y of n less than bx summation k equal to minus infinity plus infinity h of k with summation k equal to minus infinity plus infinity h of k less than infinity. that h of k value is ready to measure. That h of k is equal to 0 for k less than 0. K less than 0. That's why, and what do you call, LTI system is causal if like y of n, the response of what you call LTI system is like this. You can consider this as the causal system or casual system. Next, coming to the stability condition. Yeah, in stability condition always we require, so within this a linear time invariant system is stable if and only if, what do you call, S is equal to that stable condition or stability, followed by S is equal to the summation k equal to minus infinity plus infinity h of k mod h of k less than infinity. Okay, yeah, there is a sufficient with the help of this, where y of n is ready to measure, where y of n is equal to what you call that y of n is equal to mod, so is equal to the summation k equal to minus infinity to plus infinity h of k, okay, h of k into x of n minus k, okay, of that, how it is either with h of k into x of n minus k, or it is involved with what you call bx h of k and so on. Okay, so like this, the necessity, let us assume that s is equal to infinity. So the stability is infinity. Yeah, if the stability is, if constant, it is constant. We know that all. Where s is infinity, take the input with different values, where x of n value, where h of n equal to 0, h of n is equal to h of n not equal to 0. The time if the h of n is equal to 0, what will the output response? How it is values. Okay, like this, unbounded or output response will be like this. Next, causality condition or causality condition. The condition is followed by h of n is equal to 0 for n less than 0. Okay, so here y of n is equal to, we know that is all this, just now we have verified the output response of this, where y of n is equal to the summation k equal to minus infinity to plus infinity x of k into h of n minus k is equal to the summation k equal to minus infinity plus infinity. If you are substituting this n, where x of n minus k, okay, into that what you call h of k, like this, we have to verify that y of n, where y of n is equal to that summation, where k equal to minus infinity to plus infinity, where here x of n minus k, okay, h of k plus, so we cannot that what you call plus the summation where k equal to 0 to plus infinity, where x of n minus k h of k, like this. Right, to verify here. Okay, here this value is 0, where x of n, this value is assigned the 0 plus summation here h of n. So y output response, y of n is equal to the summation k equal to 0 to infinity x of n minus k into h of k. Like this, the condition is, we will write to evaluate by using the h of n is equal to 0 for n less than 0. Okay, so neither necessary nor sufficient condition for all systems. So, but necessary and sufficient for linear time invariant systems using this all mathematical analysis, causality condition. So, but x of n minus k for k greater than or equal to 0 shows the future value of x of n. Due to this, we require this type of condition, what we call causality condition. If h of n is equal to 0 for n less than 0, there may be what you call neither necessary nor sufficient condition for all system, but necessary and sufficient for a linear time invariant system. That is x of n minus k for k greater than or equal to 0 shows the future value of x of n. So y of n depends only on the future value of x of n. So this output response of this, so depends only on the future value of x of n. Here next, linear constant coefficient difference equation. An important class of this linear time invariant system of the form is what you call summation equal to 0 to n a k y of n minus k is equal to summation k equal to 0 to m b k x of n minus k. For this case, the output is not uniquely specified for a given input. The initial conditions are required: linearity, maybe in time invariant, and causality depends on the initial condition. So if the initial conditions are assumed to be a 0, system is linear. Okay, linear, time invariant, and causal or casual. So we can consider best example is moving average. Moving average, that y of n output response y of n is equal to x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3 plus x of what you call x of n minus 4 and so on. Okay, like this. If moving average, so you can measure that a moving average within this important LTI system of the form and follow. The output is not unique, especially for the given input or initial conditions are required. After that, we can decide the factor. You are ready to observe the causal, depends on the initial conditions. If initial conditions are assumed to be 0, system is linear, maybe assumed to be system is time invariant and causal or casual. Okay, system. Okay. Next, linear constant coefficient difference equations. Here, there I give that input is available, x of n, output is y of n. Within this, the summation k equal to 0 to capital N, a k y of n minus k equal to summation m equal to 0 to m to bm x of n minus 1. So like this here, y of n is equal to the accumulators are y of n minus 1 is equal to summation k equal to minus infinity to plus infinity n minus, so that n minus 1 x of k. Here y of n x of n plus the summation, the same value, it is x of n plus y of n minus 1. It is observed here. Therefore y of n minus y of n minus 1 is equal to x of n. Okay, this linear constant coefficient difference equations should follow. Input is x of n, where output is y of n. Okay, where x of n is the difference of y of n. Okay, so frequency domain representation. Input is x of n. How we are represent the frequency representation? E power j omega n for minus infinity less than n less than infinity complex exponential. That about the output response. Y of n is equal to summation k equal to 0 to minus infinity plus infinity h of k e power j omega n minus k. Okay, so we can define that h into, in terms of that what you call a frequency domain representation, that h into e power j omega is equal to the summation k equal to minus infinity plus infinity h of k e power minus j omega k. Okay, so e power j omega eigen function of the system, h into e power j omega is eigenvalue. So at the time of the output response, y of n is equal to, where y of n is equal to h into e power j omega into e power j omega n. Okay, like this. can what is the ideal delay, and when e power j omega is inputted, after that impulse response will be calculated. Okay, and like this can follow. Next, coming to the eigenfunction of the linear time invariant systems. So what are the eigenfunctions? Here, complex exponentials are the eigenfunction of the linear time invariant systems. Complex exponentials are eigenfunctions of linear time invariant systems. Let's see what happens if we feed what you call x of n into the LTI systems. What happens? Here, the eigenvalue is called the frequency response of the system. That's why they're using eigenfunction of the linear time invariant system. Okay, so so like this, how it is represented the complex exponential or eigenfunction of the linear time system. X of n is equal to e power j omega n. Let us see that happen. What happens if we feed x of n into a linear time invariant system? Like here, y of n is like this. Okay. Next, the eigenvalue is called the frequency response of the system. Output will be like this: y of n is equal to h into e power j omega into e power j omega n. Is the complex function of the frequency h into e power j omega. Where if you want to calculate the h into e power j omega, the summation k equal to minus infinity to plus infinity h of k into e power minus j omega k. This is the importance of this eigenfunction of the linear time invariant system. Okay, so here sometimes where e power j omega is eigenfunctions, we can represent e power minus j omega, we can represent the eigenvalues and eigenfunctions. So okay, this is the symmetric sequence functions we have to use. Okay, like exploiting the superposition of time invariance. So where x of n is equal to the summation ak x of n. The same input is given to the system, discrete time, linear time invariant system. The system is ready. Using this whole system, input is what you call x of n. That x discrete time signal x of n. We will expect this all output response is y of n. Okay. So then a set of basic signal xk of n, such that we can represent any signal as a linear combination weighted sum of these building blocks. So recollect the Fourier series. Without this Fourier series, there is no Fourier transform, isn't it? Fourier transform. After Fourier transform, we require that DFT, discrete Fourier transform. So before that, DT, FT, FT. Okay. The response of the linear time invariant system to this basic signal is easy to compute and provide significance insight. Okay, for linear time invariant system, maybe you can consider the CT, continuous time or discrete time. Continuous time signal or discrete time signal. Here it is mentioned either continuous time signal or discrete time signal. There are two natural choices for these building blocks. Okay, so DT discrete time system. So that unit pulse, it is available here. Discrete time system, continuous time system impulse. So that is the impulse from sinusoidal, or you can expect this all are okay. Later we will learn that data dependent function. They later extremely useful in the compression and pattern recognition application and so on, like image processing and pattern recognition. ANN, artificial neural networks, artificial intelligence. We require this exploiting the superposition and time invariance. Okay. So here representation of discrete time signal using the unit impulse. Okay. Yeah. Response to the discrete time linear time invariant system in terms of the convolution. Okay. So we'll continue next class. Stop this.
Like, share and subscribe. Hit the bell icon for more updates.